Okay, so far we have been doing differentiation, and differentiation means what? It's the process of taking derivatives, right? So far, if you are given a function, you are asked to find the derivative of that function. You use the product rule, the chain rule, and sum rule, and all those rules to find the derivative of that function. And in chapter 3, of course, you looked at some applications of those derivatives. So you looked at how we can use the derivative in optimization problems and in sketching curves, the graphs of functions. But now we are going to look at the opposite process of differentiation, okay? And because of that, we are going to call that differentiation. So this is the anti-differentiation. So this is the opposite process of taking derivatives, okay? So far you are given a function capital F, and you are asked to find the derivative of that function, and you find the derivative function, which is, let's denote that by lowercase f. So lowercase f, so if I have f prime is f, here we say that f is, the lowercase f is the derivative of cap f, and the the cap f is the antiderivative of lowercase f. Is that making sense? So capital F, if the derivative of cap f is f, we say that capital F is the antiderivative of f. The process of differentiation, we have seen that, and we know how to take, I hope all of you know how to take derivatives by now. And it turns out that taking antiderivatives is a little bit harder, okay, than taking derivatives. So let's look at an example. Let's say I have the function f of x, lowercase f, is the function x, okay? And I ask you to give me an antiderivative of this function. So give me a function whose derivative is x. Give me a function whose derivative is x, yeah. Well, you're going ahead of us, so let's just say half of x squared, okay? So half of x squared, notice that if I take the derivative of half x squared, I get exactly x, right? Half times 2x, which is x. So that means that half x squared is an antiderivative of x, right? You agree with that? But that's not the only antiderivative of x, okay? So notice that there are many other antiderivatives of x. Well, one of them, as you said, is just this. But how about half of x squared plus 1 over 5? Is that an antiderivative of x? Yeah, because the derivative of, when I added 1/5, it doesn't change the derivative of half of x squared plus 1/5. The derivative of half of x squared plus 1/5 is still just x, right? Because the derivative of 1/5 is 0, yeah. Say it again? Oh, yeah. So what's the, can you give me another antiderivative of that function? X. What would be another antiderivative of x? What's another antiderivative of x? Just add any other constant, right? So I can have half of x squared plus pi, half of x squared minus 0.005. I mean, you add a constant to half of x squared, you get another antiderivative of x. So how many antiderivatives are there? There are infinitely many antiderivatives for the same function x, right? But let me ask you this. If I give you one antiderivative of x, can you then tell me how the others look like? If I give you one antiderivative, do you know how the others look like? Yeah, because if I give you one of the antiderivatives, like half of x squared, you can tell me that every other one looks like half of x squared plus a constant, right? So generally then half x squared plus c for any constant c is an antiderivative of x, right? You agree with that? So this is I call this the general antiderivative of x. Okay, I call this the general form of the antiderivatives of my V looks like an R. Of x. Okay? And we are going to use a notation to denote this. We are going to write this sign. This is called an integral sign, and we are going to write x dx, and this symbol is denoting. Remember this symbol d dx of some function f of x, right? Some function f of x. What does that symbol mean, d dx? D dx means we are taking derivative, right? So same way, this symbol means that we are taking the antiderivative. Okay, we are taking the antiderivative of what happened? Okay, we are taking the antiderivative of x, and this is half. This is the general form of the antiderivatives of x. Okay, this is the general form of the antiderivatives of x, and notice that. How are we going to read this? Well, this is this left-hand side. I can say that I'm the antiderivative of x, okay? Or I could say indefinite integral. So this is called an integral sign, and this is also called the indefinite integral of x with respect to x. Okay? Is everybody okay with that? So that's how we read this, the indefinite integral. There is something called definite integral as well. We'll see that later. But this is so again, this symbol means I'm taking the antiderivative of. I'm trying to find the antiderivative of x. Okay. So the differentiation is denoted by d dx, right? Anti-differentiation is denoted by this sign here, integral sign. All right, so let's look at another example. Let's say I have the function x squared. What's the general form of the antiderivative of this guy? This would be, first of all, find one antiderivative. So what function can you come up with whose derivative is exactly x squared? Very good, 1/3 x cubed. That's a function whose derivative is exactly x squared. Once you find one antiderivative, you know that any other one looks like 1/3 x cubed plus c, where c is a constant, okay? So that's the most general form of the antiderivatives of x squared. And so the indefinite integral of x squared dx is exactly 1/3 x cubed plus c. Is everybody okay with that? Everybody's okay? Now, why am I using? Why do I write dx instead of writing just? Why didn't I just write this? Why didn't I write just this? Why do I care about writing dx? Well, same reason I write ddx, right? Why? And when I take the derivative, let's say, when I take the derivative of x squared, right? Why do I write that x, ddx? Why don't I just write d without the dx, x squared? Yeah. Yeah, so for example, let's say I have a function which looks like x squared plus a squared, right? So in that case, which one is the variable, a or x, right? So that's why I have to specify that I'm taking the derivative with respect to x. Okay? Is everybody okay? Same way, the problem here is that what if, so the problem with this notation is that what if I have an integrand that looks like x squared plus y squared, and then am I taking the integral with respect to x or with respect to y? Which one is the constant and which one is the variable? So if I write dx, that makes it clear. Okay? Everybody's okay with that? Okay, so that's just a comment here. And let's look at other examples. Could you tell me what's the antiderivative of cosine x? What's the antiderivative of cosine x? Yeah, the derivative of sine x is exactly cosine x. Therefore, the antiderivative of cosine would be sine plus a c. How about the indefinite integral of sine x? Yeah, so this is where someone can make a mistake. Notice that when I'm taking the indefinite integral of sine x, I am looking for a function. Whose derivative is sine, right? But the derivative of, so let's look at this. The derivative of cosine x is not sine, it is negative sine. So how would I get just positive sine x? Well, notice that if I take the derivative of negative cosine x, then I'm going to end up with a positive sine x, right? So that means that the indefinite integral of sine x is negative cosine x plus c. Is that making sense? You guys are okay with that? Okay, what's the integral of secant squared x? What's the integral of secant squared x? Anybody? What's that? Tangent, right? The derivative of tangent x is exactly secant squared. So this is what I would be getting in that case. What's the integral of cosecant squared x? Yeah, the derivative of cotangent x is negative cosecant squared, right? So if I had negative here, then I would say this, right? The derivative of cotangent is negative cosecant squared. But if I want to take plus here, then I would have to put a minus here. Okay? So the derivative of negative cotangent x is positive cosecant squared. Therefore, the antiderivative of positive cosecant squared is negative cotangent of x. Okay, how about secant x tangent x? What's the antiderivative of that? This is the derivative of what? This is the derivative of secant x. And I can do one more here. You can imagine what that is. Cosecant x, cotangent x, and this would be, even blindly we can say what that is, negative cosecant x, right? Is everybody okay? So that's the negative cosecant x plus c. Okay, unfortunately you have to remember these 6 formulas, okay? So you need to remember all these integral formulas, okay? Again, if you know the derivative formulas for the trig functions, you know this. So it's not hard to remember, given that you remember those. One of the things that I forgot to mention here is that in this symbol, when we write this symbol, we call the function for which we are finding the antiderivative, that function is called the integrand. We are going to refer to that as integrand, just to name it, okay? Jargon. So we can say that I'm taking the antiderivative of this integrand. So integrand means the function for which we are trying to find the antiderivative. Okay. Remember that we can take the derivative of a sum term by term, right? If I have a sum of functions, I can take the derivative one term at a time. Same thing is true for indefinite integrals. So number 1, if I take the integral of f of x plus or minus g of x, okay, dx, I end up with the integral of f of x plus or minus the integral of g of x. So this is telling me that I can take the derivative of a sum term by term, okay? And number 2, if I am taking the integral of a constant multiple of a function f of x, so c is a factor in the integrand, then I am allowed to take the c outside the integral sign. So I can write it as c times the integral of f of x dx. And we could do the same thing for derivatives, right? Remember, what's the derivative of 2 times x squared? The derivative of 2 times x squared is 2 times the derivative of x squared, which is 2 times 2x, which is 4x, right? Same thing happens for indefinite integrals. Any questions on that? Let's look at some examples on using them. Let's say I want to find. Oh, you know what? Before I even give you the examples, sorry. before I give you the examples, I want to write down one more theorem here. This is known as the power rule. But this is the power rule for not derivatives. This is the power rule for indefinite integrals, which says the following. If I am taking the integral of x to the r dx, that's the same as 1 over r plus 1 x to the r plus 1. But this works for any real number r except for negative 1. So if r is negative 1, this rule does not apply. Okay? If r is negative 1, this rule doesn't apply. I'm going to tell you what happens when r is negative 1. When r is negative 1, you basically get what function? When r is negative 1, you get this function here, right? Which is the integral of 1 over x dx. And when you go to calculus 2, you'll see that the integral of 1 over x dx is this. Okay? We are not going to use it here in this course, but when you go to calculus 2, you'll see that that's the case. If you are familiar with the natural log function, you understand what that is telling you. But if you don't know what's the natural log function, don't worry about it. When you go to calculus 2, they will talk about this in detail. So for now, the power rule applies as long as the exponent is not negative 1. Is everybody clear? Okay. Okay, so now let's look at the example that I wanted to do. My first example is what is the integral of 2x cubed minus 5x plus 3? Well, remember we said we can take the integral of a sum term by term. So that means that I can take the integral of 2x cubed dx minus the integral of 5x dx plus the integral of 3 dx. So this is by number 1 of the first theorem that I gave. And then the second part of that theorem tells you that if you have a constant factor in the integrand, that can be taken outside of the integral sign. So this is 2 times the integral of x cubed dx minus 5 times the integral of x dx. Here I don't have to take out the 3, but I will. Then I have 1 dx inside. Most people would not write 1 here, okay? They will just write integral of dx. But that means 1 dx, okay? And okay, now I can apply the power rule, right? So by the power rule, what's the integral of x cubed? 1 over 3 plus 1 x to the 3 plus 1, right? Minus 5 times 1 over 1 plus 1 x to the 1 plus 1 plus 3 times what's the integral of 1? Give me a function whose derivative is 1. X, right? The derivative of x is 1. So plus a c at the end. And what is that? Well, this is 2 divided by 4 x to the 4 minus 5 divided by 2 x to the 2 plus 3x plus c. And finally, this is a half x to the 4 minus 5 half 5 half x squared plus 3x plus c. So that's my final answer. Is everybody okay with that? Okay, that was a boring example, so let me show you two more examples here. What's that? Well, depends on how you see it. I'm saying this. The next two would be more interesting in the sense that that's what you might want to expect in the upcoming event. Okay, so I'll show you two problems that I usually ask, and so in that sense, it's more interesting. Okay, so. All right, so everybody should love math, right? No? Okay. All right. As long as you love math until you're done with all your math courses, that's fine. Okay. Once you're done with all your math courses, then you can hate math as much as you want to. Okay. But until that time, try to convince yourself that you love math. Okay. So here's a. Exactly, yes. So this is the function that you want to integrate here. So this is you're taking the integral of root x plus 1 over root x. Okay, so how would I do this problem? Well, root of x is the same as what? X to the half, and 1 over root x, that's the same as actually negative half, right? So once I have written each term as a power of x, I can just apply the power rule, right? So I can take the integral of x to the half dx plus the integral of x to the negative half dx. And then what's the derivative? This would be, sorry, not the derivative, integral. It will be half plus a 1 here, x to the half plus a 1, plus 1 over negative half plus a 1 times x to the negative half plus a 1. And then at the end I'm going to add a c. You might ask me, why didn't I add a c for each of the integrals, right? I could have added a c for the first one, right? And then I could have added a c prime for the second one. So I could have written two different constants, right? But that's redundant. The reason is, remember what c represents is that c represents any constant. So once you find one antiderivative, you are adding a c so that represents all the antiderivatives, right? So if I have a c and a c prime, well, c plus c prime, that just represents a constant, okay? Any constant. So this is redundant to write two of them. So we are just going to write one. Okay, and now I have to simplify what I have here. In the first case, I have 1 over what? 3 half. X to the 3 half. In the second case, I have 1 over 1 half. X to the 1 half plus a c. And then I get 2/3 x to the 3 half plus a 2x to the half plus a c, right? Is everybody okay with that? You guys are okay with that? Seems easy? Okay, it may seem easy, but I have seen many people missing this same problem on exams, okay? So you have to practice making sure that you know exactly what to do. Let's look at a similar problem, a little bit different, but very similar. What's the integral of t squared plus t plus 2 divided by root of t? What's the indefinite integral of t squared plus t plus 2 divided by root of t? Well, what should I do? Anybody? Very good. So write the fraction into a sum of 3, okay, and then write each term as a power of t only. So that is, you can rewrite this as t squared over root of t plus t over root of t plus 2 over root of t. And then we can say that this is the integral of t squared over t to the half plus t over t to the half plus 2 over t to the half. And now we can say that I have, what is t squared over t to the half? T to the 2 minus a half, right? 2 minus a half plus t to the 1 minus a half plus 2 times t to the negative half. So this would be integral of t to the 3 half plus t to the half plus 2 times t to the negative half. So in this case, I'm not going to write integral of the first one plus the integral of the second one plus the integral of the third term. I'm just going to find the integral of each term and write it out instead of writing one more step. So what's the integral of t to the 3 half? Okay, 1 over 3 half plus 1 t to the 3 half plus 1. So you're right what you said. Plus 1 over half plus 1 t to the half plus 1 plus 2 times t to the 2 times 1 over negative half plus 1 t to the negative half plus 1 plus the c at the end. And then what do I have? I have 1 over 3 plus 2, 5 half t to the 5 half plus 1 over 3 half t to the 3 half plus 2 times 1 over half times t to the half plus a c. And finally, this is 2/5 t to the 5 half plus 2/3 t to the 3 half plus 4 t to the half plus a c. If you could skip some of the intermediate steps, that's fine. Okay, if you want to skip some of the intermediate steps, that's fine. If you come from the first line to the last line, if you could do it, that's fine. Okay, but I wanted to write down as much as I can. Okay, so but I won't do it later. I won't write out all the steps in future. Okay, so was that example okay with everybody? Did that make sense? Again, I have asked a similar question in previous exams, and there were many people who missed it. Okay, and the only reason you would be missing a problem like this is that you didn't do the problem. I don't think this is a difficult problem. This is very, very, even if you don't understand calculus, right? You don't know anything about calculus. If somebody shows you this problem, you could do a similar problem just by knowing how this problem is done. Okay, yeah.
So, if we choose to write out all the steps,
that's fine.
At what point should we start adding the plus c?
You should always, as long as you write the plus c at the end, that's fine.
Okay, so it doesn't matter.
Yeah. Yeah. So I would be adding a c after I have taken all the integrals. Okay. All right. Here is another example. Suppose that I want to take the integral of cosine of 5x. How would you do that problem? You're saying the integral would be sine 5x, okay? Let's check. What's the derivative of sine 5x? What is the derivative of sine? Derivative of sine 5x is 5 cosine 5x, right? So what should I do to make sure that I get the correct integral? What's that? What did you say? You should be taking 1/5 right here. So notice, if I have a 1/5 here, right, then the derivative would be 1/5 of this quantity, which is exactly cosine of 5x, right? So the indefinite integral of cosine 5x would be 1/5 sine 5x plus a c. Is everybody okay with that? What do you think is the integral of cosine of a times x dx, where a is a constant, non-zero constant, let's say. So a is not 0. A is a constant number there. I mean, if a is 0, what's going to happen? If a is 0, you get cosine 0, which is what? 1. So you have the constant function 1 in that case, right? Now, if a is not 0, then you don't have a constant function. You have cosine of something like 2x, half x, 0.001x, whatever that is. What do you think is the integral in this case for any a? Remember, when I had cosine 5x, it was 1 over 5 sine 5x. So this would be 1 over a sine ax plus c. And how do I check that I'm correct? Well, take the derivative of the right hand side. What's the derivative of sine ax? It's a times sine cosine ax, right? And a times 1 over a cancels out, and you get exactly cosine of ax. So if you take the derivative of 1 over a sine ax, you get exactly cosine of ax. Again, a is a constant there. What would you say if I write this? What did you write now? What's the indefinite integral of sine ax? Very good. Negative 1 over a cosine ax plus c. Is everybody okay with those? Okay. I will see you tomorrow. Don't forget to bring your solutions for the 3 problems that I gave you, okay?